Okay, welcome back everyone to COMP2521. So how's everyone doing? All right, good. Okay. Yeah, so I'm not sure what's wrong with the left screen. So you'll have to look at the right screen. Yeah, so if you want, you can shimmy over to the right side of the theater. But yeah, hope you had a good flex week. And well done on completing assignment 1, okay? Hopefully you found it interesting. We'll release assignment 2 probably tomorrow, so you have a 1-day break from working on assignments. But yeah, so now we're going to continue on and talk about graphs. Okay, so yeah, so in this lecture, we're going to be going through some algorithms on directed graphs. So remember, just before the break, we covered directed and weighted graphs and how we represent them. So today, we're going to talk about some digraph algorithms, and also we'll talk about Dijkstra's algorithm, which will be quite useful for your next assignment. Okay, so first of all, let's recap directed graphs, right? So what is a directed graph? It's a graph where edges are directed, right? Edges have direction. So each edge has a source V and a destination W, okay? And the characteristic of directed graphs is that edges are directed. So just because you have an edge from V to W doesn't mean you have an edge from W back to V. Okay, and here were some applications that we talked about in the previous lecture. So there are lots of applications of directed graphs, like the internet, right, where we have web pages for our vertices, and our edges would represent hyperlinks between web pages, and so on. So chess, where the vertices represent board states and the edges represent legal moves. Okay, so first of all, let's talk a little bit about digraph traversal and how that compares to traversal on undirected graphs. Okay, so it turns out that traversing directed graphs pretty much involves the same process as undirected graphs. So the same process, the same code. Okay, so these are pieces of pseudocode that you would have seen in last week's lecture when we covered BFS and DFS. Yeah, any questions? Okay, so yeah, so this is the code for BFS and DFS that we saw in week 5, and it's exactly the same here. Okay. And what is an application of digraph traversal? So one is web crawling. So does anyone know what web crawling is or have heard of web crawling before? No? Okay. So web crawling is when we essentially crawl or traverse a subset of the internet, right? So you start at a particular web page, and from that web page, your web crawler is going to follow all the hyperlinks contained on that web page, right? That's going to take you to other pages. Those pages are going to contain more hyperlinks, and so on and so forth. So you're exploring kind of a sphere of the web, right, from your starting point. And there are some really important use cases of web crawling, right? So one of them is to index these web pages, right? So it's to grab all the keywords from these web pages to develop a kind of index so that when a user searches for some keywords, like in a search engine like Google, right? You can easily figure out what pages are relevant to the user's search query. Okay, so that's one really important use case in search engines. And search engines like Google typically also cache or cache these web pages. Okay, so yeah, so web crawling And with web crawling, you can choose which traversal method, right? You can choose either BFS or DFS, but BFS is likely going to be more relevant here, or more suitable. And that's because with DFS, right, what you're doing is you're looking at the first link that you find on the web page, then you follow that link, right? Then you look at the first link on that page, and then you follow that link, and so on. And if you follow that method, then you're likely going to get really far away, or you're going to get to pages that are really not related to the page that you started on, right? Whereas if you use BFS, then you're taking all the links on your first page, and you're following all of those links, right? And then you're taking the links on those pages, and you're following those links. So you're gradually getting further and further away, but you're visiting all the pages along the way. Okay, so you're more likely to get pages relevant to the page that you started on. Okay, so with web crawling, we don't really know how many web pages there are, so we can't use a visited array, right? But what we can do is use a set of visited web pages. Right, so instead of using a visited array where we start off with all the web pages being unvisited, where we have a false Boolean for each website, we would use a set. So here's what a web crawling algorithm might look like. So we give it a starting URL, a maximum number of pages to visit, because we don't want to explore the whole internet, right? We might not have enough space or time to explore the whole internet. So we give it a maximum number of pages. So first of all, we create a set of visited URLs. So that's going to be empty at first. Then we're going to add the starting URL, and then we enqueue the starting URL into our queue. Okay, and then we perform a BFS. Right, so this while loop works very similarly to how BFS works. Right? At the beginning of the iteration, we dequeue a website from the queue, and then we visit the page. Right? So that means we make a web request, right? We get all the HTML, and then we find all the links in that page. Okay, so for each hyperlink on the page, we check if the hyperlink is in the visited set, right? Have we already visited the page? If we haven't, then we're going to enqueue it and add it to our visited set. Okay, and while we're doing this, we're keeping track of how many pages we visited so far, so that we don't exceed that limit. Okay, so that's one application of digraph traversal. So what we're going to talk about next is cycle checking. Okay, so we've covered cycle detection in undirected graphs, right? So cycle checking in directed graphs is a little different. So we'll talk about how that works, but here's what a cycle is, right? A cycle is just a directed path where the starting vertex is equal to the end vertex. So there are a few differences between a cycle in a directed graph and a cycle in an undirected graph. With a cycle in a directed graph, the cycles can be any length. Okay, so you see here that this graph has 3 cycles, because we can have a cycle between 0 and 4. Right, this is length 2. Right, so in an undirected graph, we wouldn't be able to count this as a cycle, right? Because with undirected graphs, cycles had to have lengths of at least 3. Okay, then we have another cycle here of length 3, so 2, 5, 6, 2. And we have a cycle where we just have a vertex with a self loop. Okay, so 3, 3. Okay, so the question is, how do we check for cycles in a directed graph? So let's try using our cycle checking code for undirected graphs. Right, so here was our pseudocode for that. So if you don't remember how this worked, we basically modified our DFS. Right, so we did a DFS where if the current vertex has a neighbor that's already been visited, right, then you would conclude that there's a cycle. Right, so if visited W equals true in our DFS, we return true. But there are a couple of fixes that we had to make to that, right? The first one was that we needed to keep track of our previous vertex so that we don't count going back and forth along the same edge as a cycle, right? So we added a previous argument to our recursive DFS just to keep track of what the previous vertex was. Okay, and then in our outer function, so our original cycle checking function, we make sure to go through every connected component, right? Because if the first vertex if the vertex that you start from, its connected component doesn't have a cycle, you want to check the next component and the next component and so on. Okay, so the question is, does this work for directed graphs? Right, so let's try and run our code on this graph over here. Okay, so here in cycle.c, I have the same code that we use to detect cycles in undirected graphs. Okay, and in the test directory, we have a bunch of graphs. Cycle1.txt happens to be the same graph as this graph over here. Okay, so what I'll do is I'll compile program and then pass in our first graph. Okay, and it does tell us that there is a cycle. Okay, but the question is, which cycle did it actually detect? Right, so if we are starting at vertex 0, then we should end up detecting this cycle over here, right? Because we're going to do a DFS from 0, then we're going to go to 1 first. But from 1, there aren't any outgoing edges, right? So we're going to backtrack to 0, then we're going to head over to 4, and then 4 has an edge going back to 0, so there should be a cycle there. Okay, so what we're going to do is we're going to add some print statement to announce once we've found an edge. Okay, so I'm going to say found a cycle going from V to W. Okay, and at the beginning of the function, I'm going to just print out what vertex we are visiting. Okay, so visiting V. Okay, so I'm going to recompile and run it on cycle 1. Okay, so what happens? So we go from 0, so we visit 0, then we visit 1, okay, and then we visit 4, which makes sense, right? But then we visit 2, and then when we visit 1, or from 2, right, we find a cycle going from 2 to 1, which doesn't make any sense, right? So what's the issue here? Yeah?
Well, the previous thing is stopping detecting the 0 4.
Yeah, so first of all, we have one problem, which is that we're not detecting this cycle over here, right? So we go 0, 4, and then we're not detecting a cycle going from 4 back to 0. So that's the first problem. Okay, and the reason we aren't detecting that cycle is because of the previous argument. Okay, so remember with undirected graphs, the purpose of the previous argument was to make sure that we don't detect a cycle when we're going back and forth along the same edge. Right? But with directed graphs, that should count as a cycle. So what we're going to do is let's just remove that argument. Okay, and actually before we make that change, I'll show you our second test case, which is just a graph with 2 vertices where each of the vertices has an edge to the other vertex, right? And when I run our code on that graph, you'll see that it says that there's no cycle, right? So our code definitely doesn't work on an undirected graph. So first of all, let's remove our previous argument from the function. Okay, so when we remove previous, we're going to have to remove it when we call the function here. Okay, and now let's compile, and of course we've got to remove the check for if our neighbor is equal to the previous vertex from here. Okay, and now if I run my program on the simple graph where we have 2 vertices with edges going to each other, then we'll see that it detects the cycle again, right? So found the cycle going from 1 to 0. And in cycle 3, my third test case, I just have a vertex which has a self loop. Okay, that should detect, that cycle should be detected as well. Okay, so the graph contains a cycle. Okay, and if we run it on our first test case, it should also detect the cycle going from 4 to 0. Okay. So the reason this doesn't work was because of what we said before. So we're ignoring the edge back to the previous vertex. Okay. And we made that fix. So now we don't ignore the edge to the previous vertex. Okay, so here is our updated algorithm. So the question is, does this work? Well, I have some more test cases that we can try. So here's cycle4.txt. Okay, so here what we have is we've got 3 vertices, 0, 1, and 2. 0 has an edge to 1, 1 has an edge to 2, and 0 has an edge to 2. Okay? And what we're going to do is run our program on that graph. And it says that there is a cycle, right, where there shouldn't be a cycle. Right, so what's going on? So the algorithm is visiting 0, then it's visiting 1, then it's visiting 2, but then it finds a cycle going from 0 to 2. Okay, so here's the graph, and our algorithm detects a cycle, right? But there isn't a cycle. So what's wrong? So the problem is that we're doing a DFS. So starting at 0, we're going to recurse into 1, then we're going to recurse into 2, and then from 2, we're going to backtrack, right? Because there are no edges from 2, no outgoing edges from 2. So we're going to backtrack to 1, then backtrack to 0. But from 0, we're going to check this second edge going to 2. And since 2 has already been visited, we're going to say that there is a cycle. We're going to conclude that there's a cycle. Okay, but there isn't actually a cycle. So, yeah, so how do we actually fix this? So to fix it, I think we should first try to understand how cycle detection works on undirected graphs. Okay, so let's trace our undirected graph cycle checking algorithm on this graph. So suppose we start at 0. Okay, and what's going to happen? Well, first of all, we're going to recurse into vertex 1. Right, we're doing a DFS here, so we recurse into vertex 1, and the previous vertex is 0. Okay, and what's going to happen now? So we're going to recurse into vertex 2. Okay, and from vertex 2, there's an edge going back to vertex 0. So we conclude that there is a cycle. Right, but what's actually happening here is that we're detecting a cycle, and we see, and that's because we see that 0 is still on the stack, right? So when we did DFS, we started at 0, then we recursed into 1, then we recursed into 2, and we see an edge going back to a vertex that's still on the core stack, right? The function core stack. Okay, so that means that there's a cycle. But the way we check that is to check whether 0 has already been visited or not. Okay, so that's how we do it in an undirected graph. Now, if we compare that to how we check for cycles in a directed graph, let's say we start at 0 again, right? Then we recurse into 1, then we recurse into 2, then we're going to backtrack, right? Because there's no edge going from 2 to 0, so we're just going to backtrack to 1, then to 0. But from 0 now, we see that there's an edge from 0 to 2, but 2 isn't on the stack, right? So that means there is actually no cycle. But our current algorithm still says that there's a cycle because the way we check whether there is a cycle is whether the neighbor has been visited already, right? Whether 2 has been visited already. So this method isn't going to work anymore. Right, so what we need to do is to check if there's a cycle. We need to check if our neighbor is still on the stack, right? Still on the function call stack. Okay, so the way we implement that is to use a separate array to keep track of whether a vertex is on the stack or not, which is separate from the visited array. Okay, so here is the pseudocode for that. Okay, so in our main function, our hasCycle function, we're going to create 2 arrays, one for the visited array and one for checking whether a vertex is on the stack or not. And we pass them both into our recursive helper function. Okay, and in our helper function, at the beginning, we're going to mark v as being on the stack. Right, so on stack v equals true. And at the end of the function, we're going to set on stack v back to false, okay, to indicate that it's no longer going to be on the stack. Yep.
Before we backtrack, can we set visited to false instead, similar to what we did?
So before we return, can we set visited v back to false? Can we set visited v back to false? So would that work? I feel like that would work. but it would result in it being less efficient. Because let's say you have multiple paths to the same vertex, you're going to just follow all of those paths. I feel like that's what would happen. So using the on-stack array which is separate from the visited array, makes sure that you only visit each vertex once. So it's a bit more efficient. So let's modify our algorithm so that it uses an on-stack array. Okay, so we're just allocating an on-stack array, and then we're going to pass it into our function here. Okay, and then at the beginning of the function, we're going to set v as being on the stack. Okay, and when we recurse, we're going to pass that array through. And then at the end of the function, we're going to set v as no longer being on the stack. Okay, and now to check for a cycle, we're going to check if, instead of checking if w has been visited, we're going to check if w is on the stack. Okay, so if w is on the stack, then we return true. So I will just remove this if statement. Okay, and let me just make sure that this is the same. Okay, so no, so before we recurse, we just need to make sure that w hasn't been visited yet. Okay, so that should be the same now. Okay, so let's compile and run it on cycle4.txt. Okay, and if we look at our print statements, we should see that it now says the graph doesn't contain a cycle. Okay, so it visited 0, then 1, then 2, and then it would have backtracked. So just to show you that it does backtrack, I will add a print statement here. So backtracked to v. Okay, so I'll run it again. Okay, so visiting 0, 1, 2, then backtrack to 1 and 0, and the graph doesn't contain a cycle. Okay. So here's a slightly bigger graph. So let's see if our algorithm detects a cycle here. Okay, so this would be in cycle5.txt. Cycle 5. Okay, so you can just check that these edges match, and we're going to run it now. Okay, so let's see. So if we look at this graph, what should happen is that we should, supposing that we start at 0, we're going to head over to 1, right? Then we're going to backtrack to 0 because there aren't any outgoing edges from 1. We backtrack to 0, then we go to 2, then 3. Right? Then we're not going to go to 1 because we've already visited 1, but we're going to head over to 4, then 5, and then we should detect a cycle going from 5 to 2. Okay, so visiting 0 and 1, then backtrack to 0, so that matches. Then we visit 2, 3, 4, 5, and then we find the cycle going from 5 to 2. Okay, so it seems like it works. Okay, but I have another test case here, which is the same graph, except I've flipped this edge around. So the 2 now has an edge going to 5. And there shouldn't be a cycle in this graph. So if I run it now, so run cycle6.txt, it says that there is no cycle. Okay. And you can see that it backtracks all the way back to the starting vertex, right, 0, which is what should happen in a DFS. Yep.
When this is backtrack, does that mean it's going like one block down the stack?
Yeah, so it's where, yeah, so the question was, when it says that we're backtracking, does it mean we're going like back down the core stack? Yeah, so that's what it means. Yeah, so so it's like when this diagram removes the top function, right, and then removes the top function, that's what happens when we backtrack.
So the new one no longer use like a previous, does it? Or still use previous?
Okay, so actually in our algorithm, we're not using previous, so you can just ignore that. Yeah. Yeah, I'll actually remove that later. Okay, so that's cycle checking. So does anyone have any questions about that? Okay, so now let's talk about something called transitive closure. Okay, so transitive closure is kind of a similar concept to reachability. Okay, so similar thing. And the question that it's trying to solve is that given a digraph, we want to know whether a vertex is reachable from another vertex. Okay, so is vertex T reachable from vertex S? Right, and we have, we already know how to do that. Right, we can just, if we wanted to find whether T is reachable from S, what we could do is use a BFS or DFS, right, starting from S. Okay, and we already know the time complexity of BFS or DFS, right? It's big O of V plus E. But what happens if we want to answer these questions really frequently, right? So for different pairs of vertices, is this vertex reachable from this vertex? What if we had like thousands of queries or millions of queries, right? How do we do this efficiently? So we don't want to do a BFS or DFS every time, right? Because that's going to take O of V plus E time. Right? In the worst case, we might end up traversing the entire graph for each query. Okay, so what we can do to make this more efficient is we're going to construct a matrix, right, a V by V matrix that tells us whether there is a path from S to T for each pair of vertices. Right, so essentially telling us whether T is reachable from S for every pair of S and T. Okay, and this matrix is called the transitive closure matrix. Okay, and in this matrix, it's just going to be filled with true and false, my matrix of Booleans, and each cell is going to be true. So a cell is going to be true if there is a path from S to T, right? So TC, ST. Okay, so here is an example of a transitive closure matrix or reachability matrix. So on the left is the adjacency matrix for the graph, and on the right is the reachability matrix. Right? And notice that we have many more ones in the reachability matrix, because the adjacency matrix only tells us about the edges, right? Whereas reachability tells us about paths. Okay. Okay, so one way we can compute this matrix is to perform a graph traversal from every vertex in the graph. Right? We can perform a BFS or DFS, and we can just, every time we do a BFS, we fill in one row of the matrix. Right? But another way of doing it, which is much more interesting and actually much simpler, is something called Warshaw's algorithm. Okay, and Warshaw's algorithm isn't a graph traversal. What it does is it relies on transitivity. Okay, so anyone heard of the property transitive or transitivity from math? Yeah, so you might have learned about transitivity when learning about equivalence relations in Math 1081, discrete math. But the idea is, if there is a path from U to V, and there is a path from V to W, then that means there's a path from U to W, right? So that's transitivity. And Warshaw's algorithm uses transitivity to compute reachability. Right, so it applies this rule many, many times. Okay, but in order to actually use transitivity, you need some paths to exist already, right? If there aren't any paths in the graph to start with, then you can't apply this rule, right? So what are the paths that we actually get to start with when Warshaw's algorithm begins? It would be the edges, right? If there's an edge from S to T, that means that there is a path from S to T, right? So the idea of Warshaw's algorithm is that there's a path from S to T if one of these things is true, right? So if there is an edge from S to T, that means there's a path, right? Or if there is a path from S to T via vertex 0, right? So if there's a path S0T, then that means there's a path from S to T. If there's a path from S to T via vertex 0 and or 1, that means there's a path from S to T, right? So that might be a path that looks like S01T or S10T or S1T, okay? Or there's a path from S to T via 0, 1, or 2, right? So Warshaw's algorithm gradually calculates the existence of these paths, right? Every iteration, it calculates one of these points. Okay, so suppose this is our graph. Right, so there's a path from S to T if there's an edge from S to T, or there's a path from S to T via vertex 0. So here we see that there is a path from 1 to 2 via 0. Okay, so in this, I guess, second iteration, it would find out that there is a path from 1 to 2, okay, via 0. Or there's a path from S to T via 0 or 1. Okay, so in the third iteration, we would find that there's a path from 3 to 0, right? Because there's a path via vertex 1. We would also find that there's a path from 3 to 2, because we can go from 3 to 1 to 0, then to 2. And we can also see that there's a path from 3 to itself, right? Because we can go from 3 to 1 back to 3. Okay, and so on. So in the final iteration, we would see that there's a path from S to T via vertex 3. Okay, so every iteration we're admitting one vertex, right, to be used as an intermediate vertex in the path. Okay, so on the kth iteration, we're going to, the algorithm is going to check whether there is a path between two vertices using only the vertices 0 to k as intermediate vertices. Okay, so at the beginning of the kth iteration, if we have a path from S to K and a path from K to T using only the vertices between 0 and K minus 1, then it's going to detect that there is a path from S to T, right, using vertices from 0 to K. Okay, and here's the if statement that checks that. Okay, so if there's a path from S to K and there's a path from K to T, then there's a path from S to T. So we set this cell in the matrix to true. Okay, and here is the code for Warshaw's algorithm, or the pseudocode. So it's extremely simple. Right, so first of all, we create a matrix, which is a copy of A, where A is the adjacency matrix of the graph. Okay, so we create a transitive closure matrix, which is a copy of A, and then we have 3 nested loops. Okay, so our outer loop loops over all of the vertices from 0 up to n minus 1. Okay, and inside that loop, we have 2 nested loops which check every pair of vertices. Right? So for every pair of vertices S and T, if there is a path from S to K and a path from K to T, then there is a path from S to T. Okay, so what I'll do is I'll show you the code for that here. Okay, so here is our algorithm. Okay, so we take in a graph. Okay, and first of all, we're going to create a copy of the adjacency matrix of the graph. Okay, so here we're allocating our TC matrix and just copying the adjacency matrix of the graph. And here is the main part of Warshaw's algorithm, right? Just the 3 nested loops. Okay, and if we compile this now and run it, we do have a few test cases in tests. Okay, so the first one is this graph over here. Okay, so if we run our algorithm on this graph, we should get this matrix over here. Okay, so that tells us that from vertex 0, we can get to vertex 2. Okay, so that 1 tells us that. From vertex 1, we can get to any other vertex, which is true. Right, and from vertex 3, we can get to any other vertex, which is also correct. Okay, so let's actually go through the algorithm in a bit more detail. Okay, so we're going to find the transitive closure of this graph, so the same graph that we just looked at. Okay, so at the beginning, we're going to create a copy of the adjacency matrix of the original graph. Right, so here it is. We've got 4 edges, so 4 ones. And in the first iteration of Warshaw's algorithm, we're going to focus on this vertex over here, right, vertex 0. Okay? So what we're going to do is we're going to look at all the pairs of vertices that have an edge going to 0 and we're going to find all the pairs S and T where S has an edge to 0 and 0 has an edge to T. Okay? So one of these pairs, or the only pair here, is 1 and 2. Right? So this tells us that there's a path from 1 to 0 and a path from 0 to 2. Okay, so what that means is that there is a path from 1 to 2, right? So we're going to set this cell over here to a 1. Okay, and that's all we do for the first iteration. Okay, because there's only one incoming edge to 0 and one outgoing edge. Okay, so the next iteration is where k equals 1. So we're going to look at all the pairs S and T where S has an edge to 1 and 1 has an edge to T. Okay, so the first pair is 3 and 0, right? 3 has an edge to 1, 1 has an edge to 0. So that means there's a path from 3 to 1 and a path from 1 to 0. Okay, so what that means is that there is a path from 3 to 0. Okay, so we're going to set this entry over here to true. Okay, another pair is 3 and 2, right? There's an edge from 3 to 1 and an edge from 1 to 2, right? And that means we're going to add an edge from 3 to 2, right? Because there's a path from 3 to 2. Okay, and it turns out that we have yet another pair, which is just 3 and 3, right? Because there's an edge from 3 to 1 and an edge from 1 to 3. So that means there is a path from 3 to itself. Okay, so we're going to set this cell to a 1. Okay, and that's all for the second iteration. Okay, in the third iteration, k equals 2. Okay, so that means we're going to find all the pairs S and T where S has a path to 2 and 2 has a path to T. It turns out that there aren't any, so we don't need to do anything in this iteration. Okay, and the fourth iteration is where k equals 3. So we're going to find, again, all the pairs S and T where there is a path from S to 3 and a path from 3 to T. Right, and the only pair is this. 1 and 1, right? So there's a path from 1 to 3 and a path from 3 to 1. So we're going to mark this cell as true to indicate that there is a path from 1 to itself. Okay, and that's the end of the fourth iteration, and that's the end of the algorithm. Okay, so the solid lines here are the edges of the original graph, and the dashed lines are the additional edges that we've added, right, which indicate that there is a path from A to B, okay? Okay, so let's take a bit of time to analyze the algorithm. So analyzing the algorithm is quite simple because it's just 3 nested loops, right? And all of these loops iterate over all of the vertices of the graph, right? All V vertices. So that means the time complexity is going to be big O of V cubed, okay? In terms of the space complexity, it's going to be big O of V squared because we're creating a matrix, a V by V matrix. Okay, but if instead of creating a copy of the original adjacency matrix, you overwrite the matrix, then the space complexity would be O1 because you're not really using any additional space. Okay. So the time complexity is high, right? It's O of V squared, but there is a benefit, which is that you can now compute reachability in O1 time, okay? So, you know, it's a trade-off, okay? So you're trading a slow initialization or setup for fast queries later on. And the other thing is that it assumes that you're not modifying the graph, right? Because if you add one edge to the graph, that might change a lot. in terms of reachability. Okay, so does anyone have any questions about Warshaw's algorithm? Okay, so if not, here are some other algorithms for your curiosity. So we did briefly introduce the idea of strongly connected components in the previous lecture, and here are some scary sounding algorithms to compute those. So Kosaraju's algorithm and Tarjan's algorithm, you might learn these in future courses if you take them. All right, but otherwise, that is digraph algorithms. Okay, so after the break, we're going to switch gears and talk about Dijkstra's algorithm, which is an algorithm on weighted graphs. Okay, so we'll take a 8-minute break, and we'll come back at 12:05. Okay, so let's get back into it. Okay, so what we're going to talk about in this hour is an algorithm on weighted graphs called Dijkstra's algorithm. Okay, so we saw last week that BFS lets us find the shortest path in an unweighted graph. Right, so the shortest path from one vertex to all the other vertices in the graph in terms of the number of edges or the number of vertices. Right, but what happens if you have a weighted graph? Right, then in a weighted graph, the shortest path might not be the one that has the fewest edges. Okay, so we'll see how we can use a different algorithm to calculate shortest paths in weighted graphs. Okay, so in a weighted graph, edges have weights. Okay, and the cost of a path is the sum of the weights of the edges along that path. Okay, so the cost of this path, for example, is weight 1 plus weight 2 plus blah, 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 plus weight m, right, where m is the last edge. Okay, and the shortest path between two vertices, S and T, is the path from S to T with the minimum cost, right? Straightforward. Okay, and there are multiple kinds of shortest path problems, and there are different algorithms for solving these. Okay, so the first one is source target. So maybe you just have two vertices, a source and a destination, and you want to find the shortest path from the source to the destination. Okay, so that's source target. You've also got single source. Okay, so you have a source vertex, and you want to find the shortest path from the source vertex to all the other vertices in the graph. Okay, and then there's also all pairs, which is for every pair of vertices, S and T, we want to find the shortest path between each of them. Okay. So the problem with shortest path is that in a weighted graph, BFS might not necessarily give us the shortest path. Okay, example is in this graph here. So let's suppose we start at vertex 0 and we want to find the shortest path, right, from 0 to every other vertex. Well, if we just use a BFS, then we would say that the shortest path from 0 to 1 was this edge here from 0 to 1. Okay, but the cost of this path is 5, right? And we can clearly see that there is a shorter path, which goes from 0 to 2, then to 1. Right? The cost of this path is 2 plus 2, which is 4. Okay. Another example is the shortest path from 0 to 3. Right? It's not the path that has the least edges, which is from 0 to 2 to 3, but it's the path from 0 to 4 to 5, then to 3, which costs 3 instead of 4. Okay, so the algorithm we're going to use to calculate the shortest path in a weighted graph is Dijkstra's algorithm. Okay, and the one limitation of Dijkstra's algorithm is that the weights of the graph have to be non-negative. Okay, otherwise it might not work. Okay, so just to go over an overview of Dijkstra's algorithm to help you get an intuition of it. Suppose we have these locations, okay, and so we've got home, shop, movies, a restaurant, school, park, and station, right? And we're at home currently, right? And we're trying to find the shortest path to the station, okay? So the way Dijkstra's algorithm works is it's an iterative algorithm, right? So every iteration, we're going to explore one vertex of our graph, right, one place, and we're going to examine all the edges from that vertex. Okay, and gradually we're going to build up our knowledge of the graph, and we're going to gradually find the shortest paths to each vertex. Okay, so we're currently at home. So what edges are connected to our house? Right, so turns out that we have 3 edges. Right, we've got an edge going to the shop, 1 to the restaurant, and 1 to school. Okay, and that means we now have 3 locations we can go to. All right, so what we're doing is we're acting as like the GPS, say, right, that's trying to find the shortest path. Okay, so currently we have a path to the shop, which costs 4, we have a path to the restaurant, which costs 10, and we have a path to the school with weight 7. Right, so if we're trying to find the shortest path to all of the vertices, but importantly the station, which place should we explore next? Yeah, the shop, right? That makes sense because it's the closest vertex to us. So what we'll do is we'll visit the shop, right? And the reason we're visiting the shop is that, well, there is no shorter path to the shop, right? We know that there isn't because if we try to go to the shop via a different route, via the school or via the diner or the restaurant, we know it's going to take longer, right? We already know it's going to take longer because these edges have a greater weight than this edge here. So we're going to explore the shop, okay? And these orange edges, so these edges tell us what is the shortest path to each place that we know of so far. Okay, so it's not guaranteed to be the shortest path, but it's the shortest path that we know so far. And the green path at the green edges are guaranteed to be part of the shortest path. Okay, so we know that this is the shortest path to the shop. Okay, and from the shop we see that we have 2 edges or 2 roads, right? One going to the movies and one going to the restaurant. Okay, and we actually gain some more information about the shortest path, right? Because we see that we now have a shorter path to the shop, right? So this path over here from the shop to the restaurant costs 9. So we update our information about the shortest path to the shop, to the restaurant. And we also learn a path for getting to the movies. Okay, so cool. So here are 3 locations. So which location should we go to next? What do you think? So we're trying to find the shortest path to each location. Which location should we explore next? So hands up if you think the movies. Okay, so that's a lot of you. So you're right. So it's the movies, right? Because what is the cost of getting to the movies? Well, it's going to be 6, right? Whereas the cost of getting to the restaurant is 9, the cost of getting to the school is 7. So the movies is the cheapest to get to. So we're going to explore that vertex next. Okay. Right, so from the movies, we have an edge going to the diner, right, which costs 6, and an edge going to the station, which costs 8. Okay, and if we try to get to the diner via the movies, right, so we're trying to use this new road that we've discovered, well, it's going to take longer than if we just take this road over here. Okay, so that means we kind of disregard this edge, but we do take this edge into account because we haven't figured out a way to get to the station yet. So we're going to we're going to take this edge into consideration. Okay, and the next place that we're going to explore is going to be the school, right? Because it costs 7 to get there, compared to 9 for the diner and 14 for the station. Okay, so we're going to explore the school. We see that it has only one edge to the park. Okay, and what's the next place that we visit? Yeah, so it's going to be the diner, right? Because out of the 3 remaining places that we have yet to visit, it's the cheapest one, right? So 4 plus 5 is 9. So we're going to explore the diner, and we see that it has 2 extra edges, so 1 to the park and 1 to the station. Okay, and since this new path to the park via the diner isn't cheaper than our existing path, right? So the new path costs 11, whereas the existing path costs 10. We disregard this edge. Okay, so, and same for this edge over here. So the existing, actually, no, so this new edge, so the new path to the station via the diner costs 13, right? Whereas this path here costs 14. So we do update our information about the shortest path to the station. Okay, and the next location that we visit is the park. Okay, because it costs 10. So we visit the park, and now if we see an edge from the park to the station which costs 1, then that's going to be a cheaper path, right? Because this path is going to cost 11, whereas this path costs 13. So we update our information of the shortest path, and then finally we visit the station because it's our last location. Okay, so that's how Dijkstra's algorithm works. At every iteration, we're going to visit the vertex, which is the closest to us that we haven't visited yet. Okay, and we explore all the edges from that vertex, and we update our information about the shortest path if we find a shorter path. Okay, so there are 3 data structures that we use in Dijkstra's algorithm. There's the distance array, right? So this keeps track of the shortest currently known distance to each vertex. There's the predecessor array, which is used to keep track of the predecessor of each vertex. So we learned about the idea of a predecessor in week 5. Okay, so it serves the same purpose in Dijkstra's algorithm. And we keep track of our set of vertices that we haven't visited so far, or that we haven't explored so far. Okay. So here's the algorithm. So instead of reading all of this, I'll just go through the main points. So we create actually I will kind of read through it. So we create and initialize our data structures. So our distance array is going to be initialized to infinity, okay? Because we haven't visited any of the vertices yet, okay? And to actually implement this in C, there is no infinity in C. So instead, you can use int max, okay, which is the largest possible integer. Okay, next we create our predecessor array and initialize that to -1, right? Just like with BFS or DFS. And then we initialize our set of vertices to contain all the vertices of the graph. Okay, then we're going to set the distance of the starting vertex to 0, because the distance from the starting vertex to itself is 0, right? And then we're going to check So while our set of vertices is not empty, we're going to remove the vertex from the vertex set with the smallest distance. Okay, so out of all of the vertices that we haven't explored yet, we're going to pick the one that has the smallest distance, and then we're going to explore all of the vertices from that vertex. Okay, so for each edge from that vertex, VW, we're going to check if this edge gives us a shorter path to W compared to the path that we have so far. Okay, so if this edge lets us have a shorter path to W, and then we update W's distance and predecessor. Okay, and this process is called edge relaxation. Okay, so just to expand on how edge relaxation works. So during the algorithm, the distance array and predecessor arrays don't necessarily contain the most accurate information, right? They only contain the shortest path that we've discovered so far. So we need to update this information if we find a shorter path to any vertex. Okay, so during the algorithm, we're going to be considering edges. Right, so suppose we are considering this edge here from V to W, and suppose that S is our starting vertex. It's our source vertex. Okay, so when we're considering VW, we'll have calculated some information already, right? So distance V is going to be the length of the shortest known path from S to V. Distance W is going to contain the length of the shortest known path from S to W. And it might be infinity because we might have not found the path to W yet. Okay, so in edge relaxation, we're going to take the shortest path from S to V, and we're going to use this edge to give us a new path from S to W. Okay, so now we have two paths from S to W, one which goes from S to V, then to W, and one which goes from S to W without using V. Okay? Right, so we have these two paths, so the current shortest known path and the new path. And we just check if our new path via V is shorter than the currently known shortest path. Okay, so here's the if statement. So if distance V plus weight is less than distance W, then we update distance W to dist V plus weight. Okay, and then we set the predecessor of W to V. Okay, and here are some examples of edge relaxation. So suppose that at the moment we have we've calculated that the distance from S to U is 5. Okay, and then we're considering this edge from U to W, which has weight 7. Okay, and we haven't discovered a path to W yet. Okay, so the distance array, so the distance to W is currently infinity. Okay, so when we relax along this edge from U to W, we find that we have a new path from S to W, which has weight 12, which has cost 12. Okay, so we store that in our distance array because 12 is obviously smaller than infinity, and we update the predecessor of W to U. Okay, so that's an example where we haven't actually found a path to the vertex yet. But here's another example where currently the shortest known path from S to W is 12. Okay, and the predecessor of W is U, and we have we've also calculated that the shortest path from S to V is 8. Okay, so now we're considering this edge from V to W, whose weight is 3, and we see that this gives us an actual shorter path from S to W, right, which costs 11. Okay, so after we relax along this edge, we'll have updated the distance to W to 11, and we'll have also updated the predecessor of W to V. Okay, so that's how edge relaxation works. So does anyone have any questions about that? Okay, so if not, here is the pseudocode for Dijkstra's algorithm. So this isn't the whole pseudocode. There is pseudocode for edge relaxation on the next slide, but what this part contains is the initialization. So we're creating all of our data structures, setting the distance of the starting vertex to 0, and then we have our main while loop. And so while our vset, our set of all the vertices that we haven't explored yet, is not empty, we're going to find the vertex in the vset which has the smallest distance. We're going to remove that vertex from the vset, and then for each edge from V, we're going to relax along that edge. Okay? And by relaxing along that edge, this is what we do, right? So we check if this new path from S to W via V, if that is cheaper than the currently known shortest path to W. Okay. Okay. Yeah. Question. So by relax along VW weight, we're performing edge relaxation. Okay, so basically we perform this if statement. Okay. Well, it's not necessarily a function. It's just a. So you could essentially replace this line with these 3 lines here. Okay. Okay, so let us now go through this example. Okay, so we're starting at vertex 0, and we're trying to find the shortest path to every other vertex in the graph. Okay, so we've got our distance array, right, initialized to infinity, except for our starting vertex, which is going to be 0. The predecessor to all the vertices is initially -1. Okay, and here is the main loop of Dijkstra's algorithm for reference. Okay, so in our first iteration, we're going to remove vertex 0 from our vset, right, because that's our starting point. And we're going to explore 0. So we're going to consider each of these edges. And in the first iteration, since we haven't actually seen any of these vertices yet, we're going to be updating the distance and predecessor of all of these vertices. Right? So if when we relax along 0, 1, right, we're going to see that we have a new path from 0 to 1, which costs 14. Okay, and that's smaller than infinity, right? We haven't seen 1 yet, so we're going to update the distance to 14, and we're going to update the predecessor to 0. Okay, and we're going to do the same thing for 2 and 3. So we'll relax along 0, 2, right? That gives us a new path to 2, which costs 9, which is smaller than infinity. So we update our distance and predecessor. And same thing for vertex 3. So the new path, we have a new path to 3, which costs 7. Okay? So that's what happens in the first iteration. Okay, so the second iteration is where things get a little more interesting. Okay, so so now we have to remove the vertex from the vset that has the smallest distance. Right, so since 3 is the vertex with the smallest distance. We're going to remove that. Okay, and we're going to explore these 3 edges. Okay, so the first one is 3 to 0, right? And we actually don't need to explore this edge, or we don't need to relax along this edge, because we've already removed 0 from the V-set, right? Once we remove a vertex from the V-set, we're guaranteed that we already have the shortest path to that vertex, so we don't need to consider it again. Okay, so we can ignore this edge and move on to 3, 2. Okay, so when we relax along 3, 2, we're essentially asking, is this new path that we've discovered at 2 shorter than the existing path, right? The existing path from 0 to 2 costs 9, right? And the new path would cost 17, right? Because it's the distance from 0 to 3, which is 7, plus 10, which is 17. So that's not cheaper than 9, right? So we're going to just ignore that. Okay, so yeah, it's not smaller than 9, so we're going to ignore it and move on to the next edge. So this edge over here costs 15, right? And we haven't actually seen 5 yet. We haven't visited 5 yet, right? And the cost of this new path is 22, right? Because it's 7 plus 15. Okay, and since that's smaller than infinity, we're going to update our distance to 22 and update the predecessor to 3. All right, now we're done with 3. So now we're going to remove 2. So the next vertex we're going to remove is 2, because out of these 4 vertices, it's the one with the smallest distance. Okay, so we remove 2. And 2 now has 4 edges, 2 of which we need to consider, right? So we can ignore this edge going back to 0 because we've already removed 0 from the V-set. Okay, and let's look at this edge now. So we have an edge from 2 to 1, which costs 4. Right? And this gives us a new path from 0 to 1. Right? The existing path we have costs 14. Right? This new path costs 13, right? Because the path from 0 to 2 costs 9, and the path from 2 to 1 costs 4. The edge from 2 to 1 costs 4. So the cost of this new path is 13, right, which is smaller than 14. So what we're going to do is update our distance array to 13 and update the predecessor to 2. Okay, so next edge, we can ignore this because we've already explored 3. And finally, we have an edge from 2 to 5, which costs 3. Okay, now the existing path to 5 costs 22, right? But this new path costs 9 plus 3, which is 12, okay? So since that's smaller than 22, we're going to update the distance to 12, and we're going to update the predecessor to 2. Okay, so can someone tell me which vertex we should visit next? Yeah, so it's 5, right? So out of these 3 vertices, 5 is the one with the smallest distance. Okay, so we remove 5 from the V-set. Now we have 3 edges. We only need to consider one of them though. Okay, so we can ignore this edge because 2 has been explored, and we can ignore this edge because 3 has been explored. So we relaxed along 5, 4. Okay, now the edge gives us a new path from 0 to 4, right? And the cost of this path is Well, it's going to be 12, which is the distance from 0 to 5, plus 8. Okay, so that's 20. And since we haven't found a path to 4 yet, we're definitely going to update our distance and our predecessor. So the new distance is 20, and the predecessor is 5. Okay, now we're done with 5. So now we've got 2 vertices left, 1 and 4. Right, the one which costs the least is 1, so we're going to remove 1 from the vset. And we're going to explore these edges. Well, we only need to explore one of them, because 0 and 2 have both been visited or explored. So now we relax along this edge. Okay, so what is the cost of the new path from 0 to 4 using this edge here? Yeah? Sorry? 19, so it's not going to be 19. Close though. Any other guesses? Yeah, so it's going to be 18, right? And the reason it's 18 is because the shortest path from 0 to 1 is 13, right? So it's going to be 13 plus 5, okay? So when we're relaxing along a particular edge, remember to calculate the cost of the new path. Let me go back to edge relaxation. Right, so, okay, no, yeah, let me go back to edge relaxation. So when we calculate the cost of the new path, right, we're getting the distance we're getting the shortest distance to V from the distance array, and we're adding on the weight of the edge, right? So going back to our example, when we're relaxing along the edge from 1 to 4, okay, we're adding the cost of the path from 0 to 1 in the distance array, which is 13, to the weight of the edge, which is 5. Okay, so 13 plus 5 is 18. So since 18 is smaller than 20, we're going to update our distance to 18 and update our predecessor to 1. Okay, and finally, we remove 4 from the vset. That's the only vertex remaining. And we've actually explored all of its neighbors already. So we can ignore both of those edges, and we're done with exploring 4. Okay, and now we're finished with the algorithm. Okay, so that's the example, and these slides just kind of skip through each iteration so you can see the result at the end of each iteration. All right, and this is the end result. Okay, so here are all the edges that are used in the shortest paths from 0 to each to every other vertex. Okay, so now that we've ran Dijkstra's algorithm, how do we actually get the shortest path to each vertex? Right, well, you can do it the same way as you do in BFS. Right, so you can just use the predecessor array, right, and just trace backwards through it. So let's go through this example. Suppose we want to find the shortest path from 0 to 4. Right, well, the predecessor of 4 is 1. Okay, so that means on the shortest path from 0 to 4, the vertex just before 4 is going to be 1. Now the predecessor of 1 is 2. Okay, so before the 1, we'll visit 2 first, and then the predecessor of 2 is 0. Okay. So the shortest path from 0 to 4 is 0, 2, 1, 4. Okay, so that's how we find the shortest path. Okay, but important thing to note is that if you want to find the shortest path from any other vertex to any other vertex, right? So a vertex that isn't 0 to any other vertex, then you'll probably need to rerun Dijkstra's algorithm, right? Because Dijkstra's algorithm only tells you the shortest path from the starting vertex to all the other vertices, right? It doesn't tell you the shortest path between any other pair of vertices. So you would need to rerun Dijkstra's algorithm. Okay, so now what we're going to talk about is a few implementation details. Okay, so in the pseudocode or in the algorithm, one part of it which was kind of abstract was the set of vertices. All right, so how do we actually implement the set of vertices? Well, there are a couple of different ways we can do it. Right, we can use a visited array. Okay, so how that would work is we would have an array of Booleans, right? Just like in BFS and DFS, where every time we explore a vertex, we just mark the vertex as visited. Okay. So that is going to have some impact on the time complexity of the algorithm, right? Because remember, at the beginning of each iteration, we need to find the vertex that has the smallest distance. All right, so if we use a visited array to implement our set of vertices, then that's going to cost big O of v, all right? Because to find the vertex with the minimum distance, we will just need to iterate over the array. Okay. Okay, another way to implement the set of vertices is using an array or list of vertices. Okay, so an array or linked list of vertices, and the idea is pretty self-explanatory, right? So you store all your vertices in an array or a linked list. Every time you explore a vertex, you just remove that vertex from the array or linked list. Okay? And at the beginning of each iteration, what you would do is you would just iterate over that array or linked list to to pick the one that has the smallest distance. Okay, so this is also going to be big O of v, because you're iterating over the array or list. Okay, another way to implement it is to use something called a priority queue. Okay, so we haven't actually talked about priority queues yet, but we will in week 9. Okay, so just to explain briefly what it is, a priority queue is an ADT where each item has a priority. Okay, and when we insert an item, we specify what its priority is, and when we remove an item, it will automatically remove the one with the highest priority. Okay, and the way we would use it in Dijkstra's algorithm is we would use it to store the vertices and the distances to those vertices. Okay, so we use the distance to the vertex as the priority, and the smaller the distance, the higher the priority. Okay, and if we use a priority queue, we can get log n insertion and deletion. Okay. Yeah, so now we'll analyze Dijkstra's algorithm. So the analysis of the correctness I'll leave to you to read if you're interested. So the way you would prove it is by induction. Okay, but it is like a lot of reading, so I'll let you have a look at that if you're interested, but it's not necessary, or it's not assessed or anything. Okay, and now for the time complexity. So yeah, what's the time complexity of Dijkstra's algorithm? Well, first of all, we've got to consider each part of the algorithm, right? The initialization, where we create our data structures and initialize them, that's going to be big O of V, right? Because we're creating arrays of size V, setting each element, and we're also creating a set of vertices that contains V vertices. Okay, so this is going to be big O of V, and with the loop, right, we have two parts, right? We have the part which explores all of the edges of the current vertex, right? And we also have the part that finds the vertex with the minimal distance, right? We're picking the vertex that we want to explore next. Okay, so we're going to consider each of these individually. So the part that considers all of the edges connected to V, right? So if we sum up the cost of that for all of the vertices in the graph, that's going to be big O of E, right? Because in the end, we're considering each edge once, right? Or twice in an undirected graph. Okay, so big O of E. And the outer loop of the algorithm has V iterations, okay? And every iteration, we have to find the vertex in the V set with the minimum distance, okay? So if we use a Boolean array, then that's going to cost O of V per iteration. So the time complexity is going to end up being big O of E plus V squared, which is in total, overall, that's going to be big O of V squared. Right? If we use an array or list of vertices, then it's also going to cost big O of V per iteration. So the overall time complexity is still going to be big O of V squared. And if we use a priority queue, which is O of log V every time we try to pick the next vertex, then the overall cost is going to be E plus V log V, okay? Because we've got V iterations, so V times log V. Okay, so that's Dijkstra's algorithm. Does anyone have any questions about any lingering questions? Okay, so yeah, so that's one shortest path algorithm, right? But it turns out that we have a few other shortest path algorithms. So one of them is called Floyd-Walsh algorithm. So we're not going to talk about these, but just for your curiosity, we have something called Floyd-Walsh algorithm. So this is an algorithm that lets you calculate the shortest path between every pair of vertices, okay? So it's an all pairs shortest path algorithm, and nicely it works for graphs that have negative weights, okay? And another algorithm that you might learn later is called the Bellman-Ford algorithm, and it is a graph that works for graphs with negative weights, but it can also detect negative cycles. Okay, so that's yeah, so that's it. Does anyone have any questions? Yeah.
Could you explain what set of vertices mean? Like, what does it mean? What are we trying to put in a set of vertices?
Yeah. So what do we mean by the set of vertices? So the set of vertices is the set of all the vertices that we haven't explored yet. Yeah, so in Dijkstra's algorithm, every iteration, we remove a vertex from the VSet, and we explore that vertex. Right, so the set of vertices just contains all the vertices that we haven't explored yet.
So does that mean we have every single set of weights? So iteration wants to find all the set of vertices, right?
Can you repeat that, sorry?
So we iterate each one with a graph to find all the vertices.
Well, I wouldn't say so. So Dijkstra's algorithm takes in the entire graph, right? All the information about the graph. So at the beginning, you already have all the vertices in the graph. Yeah. Okay. Any other questions? Okay. So actually, so I do have one other thing. So it's a little announcement from a society, but I'm waiting for them to show up. So, okay, so, oh, perfect. Okay, so we have a little announcement from CPMSOC, which is Competitive Programming and Mathematics. So you can take the mic.
Thanks.
Yeah.
Thank you for the great lecture, Kevin. So CPMSOC is currently releasing Dijkstra t-shirts, which are t-shirts in the shape of CPMSOC logo, written in Dijkstra algorithm in C++. So yes, the code actually compiles, it works, it's been tested, no memory leaks, very cool shirt. Pre-orders closes this week, and yeah.
If you're interested in COMP2521, we basically run competitive programming and maths competitions. So if you're enjoying 2521 so far, it might be something that's worth looking into. All right, thank you.
Cool, thanks.
Scan to order. Yeah, that's about it. Thanks, Kevin.
All right.
Good lecture.
Thank you.
All right, I'll see you guys on Thursday. All right.